Hello, my name is Georg and I'm excited to present our latest work titled MAELi, Masked AutoEncoder for Large-Scale LiDAR Point Clouds. Self-supervised representation learning, or SSRL, via reconstruction, particularly using masked autoencoders, is a common paradigm to improve downstream 3D point cloud processing. However, typical SSRL methods overlook crucial characteristics of large-scale LiDAR point clouds, such as the sensor's limited 2.5D perception and limited angular resolution. We propose a LiDAR-aware SSRL approach that is carefully designed to adapt to these types of point clouds and pre-train 3D backbones applicable to various architectures and downstream tasks. Let's first look into the standard masked autoencoder approach. Consider that a single LiDAR sweep generates a partial 3D point cloud, only capturing surfaces which are visible to the sensor. Despite this limitation, many techniques uniformly apply the reconstruction loss across all voxels, mirroring strategies used for small-scale point clouds, which are for example generated from CAD models. However, this penalizes the model for potentially correctly reconstructing areas that are occluded or have not been sampled by the LiDAR beam. Consequently, the model might overly focus on replicating the sensor's sampling pattern, rather than learning the true underlying 3D structure. To mitigate this, we propose our LiDAR-aware reconstruction loss. Instead of penalizing all voxels, we additionally distinguish between empty voxels and unknown voxels. Empty voxels are those through which the LiDAR beams pass before hitting a surface, whereas unknown voxels remain unsampled due to occlusion or the sensor's limited angular resolution. Our approach applies the loss only to empty and occupied voxels. And by doing so, the model is not penalized for reconstructing unknown voxels, allowing it to potentially better understand the actual underlying structure. Specifically, our loss looks like this: a weighted cross-entropy loss for accurately classifying individual voxels. The weights are equal to 0 for all unknown voxels and 1 for all occupied voxels. And in order to compensate for inaccuracies due to the discrete voxelization, we reduce the loss for an empty voxel the further its center is away from the beam. This gradation is visually represented in the figure by the varying color shades. This is what our entire pipeline looks like. We train a masked autoencoder to reconstruct an input point cloud using our LiDAR-aware loss. With numerous samples from different viewpoints, the network learns to extrapolate beyond visible surfaces. Simply because over time, reconstructing an entire object, for example a car, becomes simpler than replicating LiDAR-specific sampling patterns. Once pre-trained, we utilize parts of the network weights as initialization for downstream tasks like 3D object detection or semantic segmentation. We employ a sparse decoder to reduce the memory footprint, making it possible to run our pipeline on a single GPU. Contrary to existing sparse voxel-based encoder-decoder structures for LiDAR point clouds, we need our decoder to expand beyond the active voxels of the encoder. We adopt the strategy from small-scale point cloud reconstruction, allowing each upsampling layer to expand cubically. A subsequent learned pruning layer is then applied to remove superfluous voxels. To demonstrate the difference to common masked autoencoders, here's a reconstruction result using a standard loss formulation. When applying our LiDAR-aware loss, the network starts to fill occlusion-caused gaps on walls and complete the rear side of vehicles in a meaningful manner. Our pre-training method proves to be an effective initialization strategy. When applied to 3D object detection, it shows improvements over various baselines, here on the ones dataset. We use the official U-small subset for pre-training, then fine-tune our models on the training set and evaluate them on the validation set. Besides our favorable results, this evaluation also demonstrates the strong cross-domain generalization capabilities of our pre-training approach. For second, we outperform the state-of-the-art methods even when using weights pre-trained on the Waymo dataset. When evaluating MAELi on Waymo itself, we observe significant improvements across a wide range of detectors. While MAELi's pre-trained weights are particularly effective for second, they perform comparably with occupancy MAE for center point and PVSNN, clearly surpassing methods like GCC3D or proposal contrast. Since our pre-training methodology does not depend on the downstream task, we further demonstrate its efficacy in the context of semantic segmentation. For this, we report the performance on the semantic kitty dataset. We follow the common evaluation protocol where pre-training is conducted on the complete dataset and fine-tuning is done on varying fractions of the training set. Our results, as stated here, reveal performance improvements across nearly all training set fractions, with the exception of the less reliable 0.1% setting, which means that only 17 annotated frames are used for fine-tuning. In conclusion, we introduced MAELi, a self-supervised pre-training approach carefully designed to adapt to the inherent but subtle properties of large-scale LiDAR point clouds. Our learned representations not only contribute to significant improvements in multiple tasks, but can also be visually verified. Moreover, it is easily applied to other datasets and architectures. If you're interested in our work, please go and check out our paper, and thank you for listening.